I guess we'll get started with just a quick recap. So this is the second talk. The first one we talked mainly about scale. So I just want to talk about scale for 30 seconds. This is a synapse by David Goodsell. It's a watercolor representative of a synapse that's drawn pretty well to scale. So just want to think of a 1,000,000 to 1 scale, right? So something that's a nanometer in the molecular world, I want us to think about as a millimeter. Something that's a micron or a micrometer in the molecular world, I want us to think of as being a meter. Okay, so so that we can keep thinking about these sizes as I'm talking about the chemistry, right? So these little neurotransmitters in here, in this world, they're small, right? This vesicle, we can see it and imagine that it's sort of got an appreciable size when we're magnifying by 1,000,000, and that's sort of the synapse. We can see, when we're 1,000,000x, this is what it's looking like, because I want us to sort of see these things as we go through. So I'll try and keep bringing that up, and I want you to sort of think about it and feel it as much as you can, because it lets you get a sense of what's possible and what's not possible. So I also touched on the idea of, psychiatry isn't a molecular phenomenon, meaning that it's not going to be a proton that's going to be what mood is or depression is or whatever. So afterwards, I thought about that, and I figured I should at least answer, well, why am I talking about it, right? If I'm saying that, hey, psychiatry isn't this, psychiatry isn't a protein-level phenomenon. I'll give you an example. So if we want to calculate the speed of an apple falling from a tree and hitting the ground, right, we will treat that apple as a single entity, as a particle, right? And we will treat that calculation as if it were one thing. But in reality, it's not, right? We know that the truth of the matter is that on a quantum level, it is the sum of all of the properties of every single atom that are giving us our answer. But it's much easier to do a simple, 11th grade physics calculation, treating an apple like an apple, than it is to calculate every single electron's momentum, etc. So it is the electrons and the neutrons and the protons and the subatomic particles that are ultimately giving us the property that allows us to look at an apple as an apple. And similarly, of course, it is the molecular biology that is making up what psychiatry is, and anything that changes in the molecular biology will obviously be reflected on the bigger scale. So it is these molecules that make up our phenomenon, but when we're looking at them, we're probably going to have to look at it as a level above. But understanding that's a fake distinction. It's obviously all one and the same. But for thinking's sake, it's going to be more sort of network level phenomenon when we ultimately get there. And the reason that that works is because of statistical mechanics, which is something that I wish I could just talk about forever, because it is something that's very difficult as a concept, I think, for us to understand. And it's the idea of how things come together, how numbers come together in sum, right? It's the beauty of large numbers behaving in certain ways. If you toss a coin 3 times, it's really hard to predict what's the percentages of heads versus tails. But if you flip a coin 1,000,000,000 times, the property of that system, based on statistical mechanics, is that it will behave in a certain way. So although each individual subatomic particle and molecule in here is working randomly, when we look at big enough numbers, it lets us take a step back and get rid of some of these variables, get rid of some of this randomness. And that's sort of the beauty of statistical mechanics. And we'll talk about that a little bit later, because what it allows us to do is to neglect small variables and make calculations without tons of information. All right, so I've asked this question last year, and I never got to answer it, so I figured I'd come back to it now that we're going to be moving into chemistry and physics. So I asked the question, what is Prozac and what does it do? Okay, so I just want to start with the med students in the back, or fluoxetine, right? What is fluoxetine and what does it do?
SSRI.
It's an SSRI, all right, that's the standard answer. What is an SSRI?
It's selective serotonin reuptake.
Okay, right, so that's what that stands for. What does it do?
Increases the amount of serotonin left
Okay.
in the pouch.
That's right, so you all get your MCAT, or no, I guess MCAT, USMLE question correct, right? That's what the question is going to be, and that's what the answer is going to be. But what I'm going to say is, really? Is that really what it is? Right? What is fluoxetine? So this is fluoxetine here. All right, this is when you prescribe fluoxetine. This is what your patients get, okay? They get the medicine, these pills, and they get a handout, all right? I'm gonna pass this around. These are capsules, all right? I want you to break it open and like sprinkle it out, okay? Fluoxetine in our world is a powder, okay? It's a powder of a chemical, all right? And we can talk about the way that they make it. Obviously, there's a capsule, it's a gelatin, it's got a binder on it so that it sort of can hold together and stick together. And we're not going to go too much into that. But I want you to like actually look at it, okay? So this is what fluoxetine is. And I'll just put a couple of them here. And yeah, you can pass that around as you go. So to help us really understand, you know, what is it really, right? What are we really seeing here? So what it ultimately comes down to is we're talking about symbols, right? Fluoxetine is a set of letters that means whatever we want to say it means. And then we have all these other symbols of representing fluoxetine, right? So it has an IUPAC name. RS-N-methyl-3-phenol-3,4-trifluoromethyl-phenoxypropane-1-amine, right? This lets you get this sort of little structure. This is the formula, right? If we count the number of atoms, it's got 17 carbons, 18 hydrogens, etc. This is a Lewis structure, right? It shows you how are these atoms arranged in 3D space, all right? But I also want you to realize that this is not static, okay? When this thing is living in the world as a molecule, so literally, okay, this, you know, we talked about a carbon atom being 1 angstrom. All right, so if a carbon atom is 1 angstrom, roughly how long do you think this thing is? And I also said a glucose molecule, which is a hexose sugar, right, a 6-carbon sugar, is about 1 nanometer. So if you had to guess in our little molecular world, how big is this thing?
15.
Right, so we're able to get within that range. I don't know how big it is, and the other thing is that it's moving and these things are changing, probably 2 to 3 nanometers, okay? So in our world, it's 2 or 3 nanometers, okay, each molecule. Now, this is literally a molecule, okay? It's a real thing, it has mass, it has properties, and what's inside that pill is a whole bunch of these molecules. And we could calculate it out, right? That's 20 milligrams. We could calculate, by calculating, counting the number of atoms and the weight of each, how many molecules of this are in here. Okay, so this is not some vague abstraction. There are literally X number of these molecules when you swallow the pill that go into your body. And this is not static, right? We draw it as static, but these bonds are flipping around. They're vibrating, these electrons are spinning. It's a very living, breathing kind of system. Okay. Has anybody seen this sort of thing before? Okay. This is a ball and stick model, right? What it does is it shows us the relative distances between atoms within a molecule, right? And so Linus Pauling figure out bond distances, right? It's not random. You have a carbon-carbon double bond, it's roughly the same distance in shape every time.
That's what we asked.
Some more symbolic stuff. Do you need more? Do you want to be happier? Yes. Did somebody say? I'm not going to even repeat that. No, do not take that, please.
What is this? It doesn't smell like anything or taste like anything.
Why do you want to have Prozac?
Just the part of it.
And so
Go your
here,
honors, all for you.
here is a space film model. I'm curious to hear what our conversation is about, because I want this to be interactive. What are we talking about?
Olivia wants honors on her rotation.
I said it doesn't smell like anything or taste like anything.
Okay, perfect, right? So it is a colorless, odorless molecule, right? And in fact, we could predict that. If you need your chemistry, we'll come into this. And we'll get that later, right? What are the functional groups that tend to have an odor?
Amines.
Amines possibly. There are 2 in particular that
Odors? Esters.
Esters, right? Esters tend to smell like what?
I don't remember.
Like fruity, pleasant. What else has a nasty kind of
Sulfate.
sulfur, right? So sulfur, disulfide bonds, things like that. I don't know enough about chemistry to know about sort of how things act when they start summing together. But yes, this implies certain characteristics. So this is a space-filling model, right? We're imagining that these are electron clouds showing us sort of what's going on. So now we can begin to say, what is Prozac, right? Prozac are these atoms, literally, these atoms bonded together in a particular way that have this shape, that have these charges, that give it particular properties, okay? Now this molecule is a little bit bigger, or a little bit bigger than this here, okay? So it has a size in this world. It is in this world. So now when we ask, what does Prozac do? What does it do? I haven't gotten into the science yet, but you guys know science, so how could this possibly do something?
It could bind to something and change its function.
Yes, so it has chemical properties that allow it to interact with other things, okay? Does it know to hunt down the serotonin reuptake receptor? No. So is it only going to bind to that? What is it going to bind to? Whatever the hell the chemistry tells it to bind to, okay? The serotonin receptor is going to have amino acid sequences that give it particular properties. Anything in our body that has similar amino acid sequences or chemistry that this is going to want to bind to is going to bind to, okay? So by calling it an SSRI, we are making de facto assumptions about Prozac and how it works that may or may not exist, okay? And I'm going to argue strongly that many times that is not its mechanism of action. Many times it likely is, but it's more complicated than that. So what I'm getting at is this molecule can make truly physical motor changes to proteins that can lead to changes in our physiology. All right, so on a molecular level, that's beginning to get at the rubber meeting the road of how this works. Now, how a protein conformational change can lead to a change in thoughts and behaviors, right, is going to be much trickier, and we're not going to be able to get there quite yet. We will begin to talk about how can you get properties like that from really, really, really simple things. And we have some great examples in the natural world of things like that happening, which we'll get to when we start talking about systems and networks and that kind of thing. All right, so this is a picture of, anybody know what this is? I wouldn't expect really anybody to.
Hadron Collider. Super Collider.
How do you know that? That's absolutely right. Yeah, I wouldn't have known that if I had actually typed in Large Hadron Collider. That's right, that's what it is. It's the Large Hadron Collider. I have no idea how this stuff works together, but needless to say, we're going to talk about physics now. This is going to be my weakest subject, right? I mean, I have a hard time conceptually with some of these things. I understand it basically, but it gets very complicated for me. So I might struggle a little bit with some of this, and I'll be honest with you when I can't answer or don't know. But physics is very cool, and really most of the amazing things that we have came originally from physics. It is at the cusp of creating things and doing things. That's what physics is about, understanding the environment and manipulating the environment. Okay, so now I'm going to get to a question that really is kind of near and dear to me, and that is, what is science and what is knowing? Okay, because this is something that kind of gets taken for granted and I think can create animosity between people who think differently. So what do you guys think?
What is science? I would say,
Yeah.
I would probably say like the systematic pursuit of truth.
Yeah, I think that's great. Anybody else have any other thoughts? So what is truth?
Maybe if we clarified, science could be a systematic way of getting to be able to predict patterns in the future based on patterns that you observe.
Okay. I like that a lot, right? Because truth ends up having this implication. I would call it a truth, okay? But that's my own personal thing. It might have a connotation that makes people uncomfortable, right? So what is science really getting at? It's getting at models, right? And models of what? Models of prediction, right? And how do we get these models of prediction? How do we get these models from science?
Experiments.
Experiments, right? So we try our best to look at how the world works, see the rules, see when things work, see when things don't, to learn, hey, how does all this stuff work, okay? That's what this is. It's a group of girls and guys who are like, how does this work? They're not trying to trick people, they're not trying to fool people, they're just trying to say, how does this work? You know, how can we understand this better so that we can do good or do whatever, I guess. It ultimately, to me, science is practical, okay? Even if your model is wrong, right, like the Newtonian model was incomplete, it was hugely helpful, right? He was wrong about so many things. Freud was wrong about so many things. I mean, Einstein was wrong about so many things. but they're putting forth a model that's advancing the idea of prediction. It's wrong in some places, but it begins to be more and more right the more that we look at it, okay? But there are things that science can't do, right? Science, I can't say that tomorrow gravity's still going to hold. We can't experiment on the future. All that science can do is say, hey, we've looked at this, it tends to do this most of the time, we're assuming it's probably going to keep doing this, and hey, fortunately it's worked out, right? And so I think all that science is trying to do is its best to solve problems, okay? So I kind of want you to think about it as relative truths, right? Nothing is 100%. You can do something 10,000 times and assume it's going to do the same thing the 10,001th time, and usually that's a fine assumption. But because of the way that numbers work, it doesn't have to. Right? So we're talking about relative truths. We're talking about being practical. We're talking about solving problems. And it works well enough to solve problems. Usually. Okay, so I kind of went on the side there. The other thing that I want to say is that arts and science are often things that are sort of looked at as opposite ends of the spectrum. But I want to disagree and say that art and science very much go hand in hand, right? So what is, if you have a great artist, what is that artist doing? What is she doing? Think about what great art, think of a great piece of art, whether it's film or literature or a sculpture or a painting. What does that do?
Changes the way you look at things.
Okay. It changes the way that you look at things. And what does a successful piece of art do?
Evokes emotional response.
Yeah. It gets you to feel something or see something or think about something. And usually it's trying to capture something. It's trying to capture something real, right? So it has just as much stake in understanding as science, right? Scientists use a different medium to capture something real. An artist might want to capture the death of Christ in a way that we can feel it and understand it. And that's what science is doing. We're trying to capture something to understand it, right? Dante's Inferno is capturing this feeling that does it much better than a number is going to do, right? So for different mediums, we need different things. And I think that's what it really comes down to. And you'll see that what scientists are doing is they're trying to capture something and make it get across to people. Although it's usually not as pretty as when artists do it. So I'm not going to show a lot of slides about physics, but what this picture is getting at is electromagnetic, the electromagnetic force. Okay, so there's four forces. The electromagnetic force, gravity, the strong force, and the weak force. Okay. Fortunately, we can disregard pretty much all of them when we're talking about molecules. Okay, gravity doesn't really apply because it's really tiny. The strong and the weak force we can pretty much take for granted because they just keep everything stuck together. So what we're going to be talking about is the electromagnetic force. And this is something we don't think much about, but it is responsible for pretty much everything. Okay, everything that we do, touching, pulling, pushing, friction, static electricity, chemical reactions, is all the electromagnetic force. Okay, and what the electromagnetic force is simply that through these basic rules, charge and momentum, we get these consequences of things. Okay, because electrons are charged and they have mass and they move and they either hit into things or get pulled towards things or pushed towards things. That's where our forces come from. And so this is a little bit complicated and I'm not going to go too much into it, but the force carrier, do you know what carries the force of charge? The electromagnetic force? How fast does it travel? How fast does electricity travel? I mean, it's not in a vacuum. How fast would a radio wave travel in a vacuum?
Speed of light.
The speed of light. So what do you think is carrying it? What particle?
Quark.
Not a quark. That's a pure gas, right? What travels at the speed of light? Photon. So photons are the force carriers. Photons carry the quanta of energy from these things. And depending on what type of body it is, these things emit different quanta of energy in photons, right? So we're not going to get into this a lot, but that's what's happening. We're sort of emitting photons and we're absorbing photons, and that's where our energy is, mainly when we're pulling, when we're pushing, that sort of thing. All right, so math is a pretty abstract science, right? It's probably true, right? I don't want to get too much into truths, right? But you're likely not going to be able to find a right triangle that doesn't obey the Pythagorean theorem, right? I don't think that's going to ever change, even with time. maybe someone would disagree with that. I don't think you're ever going to find a triangle in Euclidean geometry that the sum of the three internal angles is not 180. I think that just is a triangle. I have a hard time imagining not. Physics is one step removed from math, right? We're no longer abstract. So physics is getting into be a rougher science, but it's still a pretty hard science, right? Besides math, it's probably the hardest science. The further we get away from that, the softer the science is going to get. So fortunately, we don't need to think about this too much, right? We only need to know electromagnetism and electrodynamics in the sense that it's going to apply to chemistry, that we want to apply that chemistry to biology, that biology to neurology, that neurology to psychiatry. Okay, so fortunately, we don't need to think much about this. I just want to kind of introduce it in that sort of way. But what I do want to say is, I mentioned pulling and pushing, right, being the electromagnetic force. And I don't mean that in like a analogy. I literally mean, when you push something, okay, that is the electromagnetic force, okay? When I am pushing here, it is truly the molecules in my finger having an electromagnetic repulsion to this hand, okay? And the perception of this being solid, right, is totally, it's up here. We are not solid, right? Has anybody kind of gotten this blow away kind of moment yet? Like, our brain is interpreting the photons coming from our hand and creating this image of us, but we are largely empty space, okay? So, to give you an example of that, here we have a helium atom. Okay, so helium is element number 2. It has 2 protons and 2 neutrons, all right? How many electrons does it have?
None.
2.
2, it has 2, good, okay. So it's electrically neutral, right? So for every proton we need to have an electron. So the strong force is holding these things here, right? Because you can imagine these are light forces, they would otherwise blow out. But I want you to see the scale. Okay, this is 1 femtometer. This is 1 angstrom, which is 100,000 femtometers. And this is a probability cloud of the electrons, okay? So we have 4 tiny particles that are 100,000th the length of the almost diameter of this electron cloud, okay? So these are real things, okay? These have volume. They have weight. Similarly, the electron has volume and it has weight. So if this was the nucleus, okay, this was this in here, what do you guess the size of that electron cloud is?
300 miles.
It's a mile, but you're absolutely right. If that's the scale. So literally, this is
There's
here,
a lot of honors.
here to Wild Wings to Barrack Shopping Center. In a sphere, all that we have is this and 2 electrons, which are tiny, flinging around. Okay, that's us. We are poof. We are probability. Okay, what we are is potential. Okay, we are force fields. Literally, as we push, it is not matter that's pushing back. It is a force field that's pushing back. And that's the reality of things, okay? The real world is a very, very quirky place. And we don't think about those things often, but it's useful to understand that just what we see doesn't make science, right? Because it goes deeper than just what we see. We are translating things in the natural world by the time we've got them. We're not getting raw data. We're getting translated data. So it's just kind of interesting. The reason it kind of works is it moves so fast that this can almost act, right? Because matter is energy to some extent. So these electrons are moving so fast that it's almost like there's so it's denser, closer, and it's almost as if the negative charge is everywhere at once. It's moving so quickly. So if you were to stick your finger right here, you'd hit something solid because it's whipping around so fast. So that's when we start getting into this wave-particle duality kind of stuff, and I'm not going to get much into it, but it's just fascinating to think about. Joe? All right. So here we go. This is mainly where we're going to use physics. Okay, so this is, does anybody want to guess at what this is kind of getting at? What did you say? So this is the only picture I don't mind that I actually had to stretch to fit. We need this med student at every single one of these talks. What do you see is kind of happening here, based on this picture? What is it trying to get at?
forms of energy.
Conservation of
Okay,
energy.
what is so this is talking about thermodynamics, okay? Does anybody know what law of thermodynamics, the conservation of energy is? I mean, it doesn't matter, just a number.
2. Close.
One.
First, yeah, thank you. So the first law of thermodynamics pretty much says energy cannot be created or destroyed, but it can be transformed, right? So what this is showing is that whatever comes in, we have to have an equal amount. Really what the first law says is that, I guess, you know, Q equals U plus V or whatever, but pretty much getting at that whatever comes in is either going to leave or get stored, okay? And so that's what we're going to be looking at when we're talking about thermodynamics. Thermodynamics actually are important to understand how our body works, and so that's what I'm going to focus all of the physics time on. The reason that thermodynamics is important is that it's talking about work, okay? So whatever comes in can either increase the internal energy, well, energy in equals the increase in internal, or change in internal energy, plus the amount of work that we can do, okay? So we're talking about work. We are creatures of work. Everything that we do that goes against a gradient requires work. And that's where thermodynamics are going to come in. This is also where statistical mechanics comes in, okay? What's temperature?
A measure of kinetic energy.
Oh, that is absolutely right. I'm taking it one step further. It is a measure of kinetic energy of what? Of molecules, right? So temperature is not it's an emergent phenomenon, right? And the individual kinetic energy of each molecule kind of averaged out in a statistical mechanics kind of sense gives you the temperature. You cannot see the temperature and know the kinetic energy of any molecule, but you can know the kind of average energy of the system, okay? So this is, again, using quantum or statistical mechanics to not have to look at every single molecule, but to be able to just look at things in a practical way that we can do calculations. So I'll just very quickly go over the laws. So the zeroth law of thermodynamics is straightforward, right? If system A is in equilibrium with system B, and system C is in equilibrium with system B, system A is in equilibrium with system C. And does that sound familiar to anything? Right, A equals B, B equals C, A equals C. It's like the transitive property. Yeah, there's like the additive property, the transitive property. Yes, that's what it is. Very good, thank you, Joe. The first law of thermodynamics is what we said, pretty much energy can't be created or destroyed. But stated like eloquently, it's the increase in internal energy of a closed system, which is this, is equal to the difference of the heat supplied to the system, which is this, minus the work done to the system, okay? Right, so energy in minus energy out equals the increase of energy in the system. It's pretty straightforward stuff, right? And the second law of thermodynamics says that heat can't go spontaneously from cold to hot. And that's, again, a matter of statistical mechanics. In an individual case, a single molecule can, but we're talking about heat in large systems, just the numbers aren't going to let it happen. And the third law of thermodynamics just says, as a system approaches absolute zero, the entropy of the system approaches the minimum value. So we're going to talk about those things a little bit more here. All right. Does anybody remember this? Nightmares. Are we having nightmares? Yes. Okay. So this is Gibbs free energy. All right. So what we're looking at here in this picture is up here we have what's called an exergonic reaction, which means delta G is less than 0. What that means is delta G final minus delta G initial is less than 0, which means that, you know, obviously we can see here, this is less than this, so if we subtract them, we're going to get a negative delta G. This reaction will go forward, all right? So when delta G is negative, systems want to get the least amount of energy possible, okay? The world is a sloth. Things like low energy, right? We want low energy and we want equilibrium. We want low energy equilibrium. I'm going to say that sort of a bunch, and I want you to think that, because that's where things are happy. And if we think back to energy can't be created or destroyed, this change in energy is called the Gibbs, the change in Gibbs free energy is the amount of work that can be done, okay? This is the difference in energy. This is the maximum amount of work that this reaction can do. And it's non-expansion work because of the way that we set constants in this equation. And obviously, the inverse is true here, okay? So this will not proceed unless you heat it. Let me actually take it back. It goes in both directions, okay, always. But it's a statistical probability. Just like diffusion, when we talk about things diffusing, they don't know what's going on. It's just the statistics of it. But it's much more likely for this reaction to go this way than to go this way. all right? And they each do it in their own amounts. So getting down to the Gibbs free energy, what we're really sort of looking at here is that the Gibbs free energy equals the internal energy of the system, which comes from the vibration, or rather, the vibration of the molecules, the rotations of the bonds, and the energy stored in the bonds. And this is, it gets kind of complicated, but we're talking about the work to keep this at a constant pressure at a given volume. And this equation here is just a matter of how much energy you can get from the system by heating it. So some things like to be heated and some things don't. And that's a matter of entropy, which we're going to talk a good bit about, because entropy is a really, really cool kind of concept. So the most important thing here, and we're going to go over this a good bit in chemistry, and you'll understand it and kind of see what it does, is that this delta G is going to determine what direction equations want to go, what types of things equations want to do. All right, so who can define entropy?
Level of chaos?
Right, the amount of disorder. All right, so what's a simple, that's right, it's the amount of disorder in a system. Chaos, we use the word chaos a lot. Chaos means something actually different. Chaos is a sensitivity of a system to initial changes in the starting state. And what that pretty much means is that you would assume that kind of, if I dropped this marker from here, it would hit the ground at speed x, and if I dropped it from, just slightly above it, it's going to hit the ground at speed x plus just a tiny bit. But a chaotic system, this shift in tiny bit might make it negative. It might have a huge shift to it. So it's applied to nonlinear systems, where a small change in one direction might get amplified. Whereas disorder is a little bit different, but a chaotic system tends to be disordered, is why those two things often go hand in hand. So it is disordered, all right? So I got some paper that I'm going to hand out. Do y'all have pens?
Yes.
All right. If you just want to pass that out. And I've got a couple of markers here, because people don't have pens.
You need a pen?
The simplest way to think of disorder, right, or what entropy would be, is if you had to describe a system in words, how long would it take you, okay, to get it precisely described? Now, letters do an okay job, but it's not perfect. But you can imagine, and in fact, I can try and walk somebody through this, right? Do you have a pen? Do somebody want to focus on Joe and I? Joe, I use you for everything, is that okay? I'm going to get you a gift. Can you get the camera for me? Yeah. So I want you to close your eyes, Joe, and I'm going to guide your hand, okay? And based on this experiment, I want you to tell me whether we're going to have more entropy in the first or the second situation. First, I'm going to get him to draw that first letter, all right? So I want you to, you're pretty good, bring your hand down to the paper, okay? Now I want you to move your hand right about an inch. All right, now I want you to do about a semicircle, half semicircle up, and then connect it back to the other side, creating that top loop of the E.
Move back.
Back down, connect it, and then finish off the E. Okay, good. And now I want you to pick your hand up, move it to the right about 2 inches, and move it up about 4 inches, and stop, all right? I want you to get down and put a dot. All right, I want you to pick it up and go about a centimeter, put it down, put a dot. All right, I want you to go up, go over about half a centimeter,
To the
right, put a dot. Now I want you to get down about half a centimeter and right about half a centimeter. Right, okay, and you can stop. You get the idea that the amount of information to describe all of these dots, and it's not just their space, it's actually all of their properties. And so you can imagine if this E was sitting here, it's probably not moving much, it's probably not going to change much. This is probably going all over the place. So to describe the order of the system, to predict it, it's going to take way more data. And this is getting into information theory. How much information do we need about a system? Or rather, really the better definition of entropy is how much do we not know about a system? How much can we not describe about a system is the entropy. It's getting at levels of freedom, right? The more degrees of freedom something has, the more entropy it has. So a few interesting things. Entropy always goes up, okay, in a closed system. Have you guys heard that? It's one of the coolest things ever, right? Everything that we know of in physics is reversible, all right? Forces are reversible, gravity is reversible, entropy is not reversible. It only goes in one way, and that fixes time, okay? Because without that, time could be bidirectional. Time definitely goes in one direction. I can't tell you which way, but it definitely goes in one, and it's because of this entropy. It's not reversible. So, does that mean that every single reaction that occurs has to create entropy?
No.
No.
No. How is that? How can we break the? How can we break this law of thermodynamics?
It's not a closed system.
It's not a closed system. That's right, absolutely. Because we are not a closed system. We live in the world, right? So anytime we decrease entropy, we increase entropy in the world. This is a very real thing, right? So what we do as life is decrease entropy, okay? And this gets me to just a brilliant quote by Erwin Schrödinger, and I showed you his equation last time. He defined life as a system that resists decay into equilibrium. That holds for pretty much any way I can think of life. And it actually grades life on a real gradient, which it probably exists on and not this sort of artificial thing. A crystalline structure is not really alive, but it's probably more alive than air molecules, okay? We create order. That's what we do. And we are the only, life is the only thing in the universe that perpetuates order. Everything else in the universe pushes to disorder. A bunch of air molecules will never order themselves up in a fancy way. It just doesn't happen. We create order. That is what we do. And to do that, we need to get fuel from the outside, break it, and give energy to the outside. That is what life is. We are an order-creating process, right? For us to have this beauty in us, this sort of solidness, requires us to fight breaking apart. At every moment, we are repairing our body's desire to break apart. We know that, right? Our cells want to break apart and die. Proteins want to break apart and die. We are constantly fighting this process. And to do that, it requires us to do what? We need to eat, right? We need to breathe. We need to get energy from the environment to turn it into order in ourselves. And how do we disorder the environment?
Heat.
Heat. That's absolutely right. It's heat. We are constantly giving on heat. We are constantly disordering. We are disordering the environment around us more than we are ordering the environment within us. And that should be obvious if you just look at the state of affairs in the world. Okay? That's not physical, that's political. So, all right. So we got to that. Here's another question. Let's see where I want to go here. Where would the brain be on this entropy E to Y? What letter would the brain be?
E.
E. Okay. Joe says E. Any other takers?
Oh, probably T.
T. Okay. Anyone else?
Like warfare.
Go with Y.
Go with a Y. Okay. So I'm going to use those three examples, and I'm going to explain to you what I mean by what would the brain be. So E is a system that has a very typified kind of point-for-point E. What that means, and I talked about intelligence. Does anybody remember how I defined intelligence last time?
Taking information in, processing it, and then reacting.
Okay, taking in information, processing it, and then reacting. Okay, so if E was a brain, and it got two inputs. It got input A and input B. E gets input A, and it processes it out 10. It gets A, 10, A, 10, A, 10, A, 10, B, 20, B, 20, A, 10, B, 20. It is what it is. It is going to give you a one-for-one point discrimination every single time. There's no flexibility in the system. For our brain to work this way, we would need infinite neurons, okay? Because neurons would lack flexibility. We would need to have a neuron code for a face in every single angle, right? You move that face a little bit, we don't understand it anymore. It's not a 10, it's a 10.2. We can't process a 10.2. We need something else. This only understands 10, right? It can only do that. So let's look at Y. I'm going to let you guys guess what Y might be. If I said A, what's A going to be?
Would be anything.
Could be anything. A this time could be 7. A next time could be negative 14 pi squared. A next time could be 1 over 16. A next time. So what this does is it doesn't allow us to act rationally in a system. We would act randomly. There would be no order. There would be no ability to solve problems in the system. What does T do? If I say A A equals, let's say 10 is the right answer in a perfect world. A equals 10. A equals 11. A equals
10.
Right, that's right. It gives us flexibility. It allows us to create a space for error, a space for margins. And so think about when you guys want to get your credit card information or log onto a site, what's the test that they do to check if you're human?
They make you copy that, like.
Those
so
letters
like,
are
what do you
like-
think?
Wait, but they're not just letters, right? Letters are doing something. Why do they do that? Because a computer can't figure it out. Because it is very complicated. What this allows us to do is it allows us to abstract T. It allows us to say this T and other T's, right? Because this isn't the only T. It allows us to get a symbol of what T means, right? It allows us a space. I don't know if you guys came to my mind web lecture, but you can imagine a multi-dimensional space where all of our knowledge exists. This E will only code to a dot in the space. That is only one piece of information, perfectly defined. Grand mal space in this angle, in this lighting, in this place. But this T allows us to create a three-dimensional space based on the answer, roughly in this area, right? And when you get enough of these, you can sort of shape where is it, and it allows you to kind of guesstimate. And that's what we do tons of, right? We don't have 100% certainty on things. I mean, we often do, but this is what our brain wants to do. So our brain, and I said this last time, life is at the border of order and chaos, okay? This is what life is. If we want to make a computer think, we need to get away from this. We need to start programming this, and people are realizing that. You need to put error. You need to allow a computer to get outside of just straight one-to-one processing, and that's when we'll start seeing intelligence in computers. Okay. What's going on here? So this is a protein, and this is water. Why is that protein moving? Has anybody heard of what this is? I'm sorry?
Brownian motion.
Brownian motion. Can you describe Brownian motion to me? These people are so smart. What is this? I wouldn't have known this if I didn't type into Wikipedia.
It's just kind of random motion, it's like bumps and everything around.
Yeah, in a fluid.
You said random. It's not random, but it appears to be random. But you said something else. Bumps, right? That means something, right? We're not just gestalting. What is really happening here?
Any brownies?
They're all.
I mean, you know, we were pretending that these are small. This would act the exact same if we put the properties on it, and this was a tennis ball and these were ping pong balls moving, right? Momentum, mass, is hitting these things and transferring energy, and the summation of them is creating movement, okay? So when things move around in our cytoplasm, this is what is happening. Brownian motion is moving, all right? So this is fascinating to me, all right? Why are they moving at all? Why aren't they just all standing still?
It's not absolute zero.
It's not absolute zero. Okay, that took me a little while to actually think through. Why is it not absolute zero?
Because they're moving.
That's a circular argument, but that's true. So why in our world are we not at absolute zero?
There's no entropy at absolute zero. Less
Because we're not.
There's less entropy, yes.
Because it's
We're not in homeostasis.
We're trying to
Set
maintain,
motion.
yeah, we're
Okay.
trying to find out homeostasis.
Just a simple question. Why is, not even life, but if I just put a cup of water here, are the water molecules moving? Why?
It's not the end of the universe yet.
It's not the end of the universe. What are you getting at?
Expands.
What does this movement mean? You all have kind of said it. There's energy in here. Where is this energy coming from?
start of the
Universe.
universe.
Right,
Yeah.
but more practically for us, where is 99.9% of our energy coming
It's the heating mass.
Heat.
from? From
The sun.
the sun, okay? I want you all to think about that, literally. The earth is powered by the sun in a very real way. The sun bangs against our oceans, creates weather patterns. Plants take photons, literally take photons, using chlorophyll, and I forgot what the name of the proteins are or whatever, convert that to energy, okay? Animals eat that energy. Literally, we are powered by the sun, 99.9%. The sun is putting energy into this. We have a temperature. What that temperature means is that there is kinetic energy stored in these molecules. That's why they're moving. If we didn't have the sun, they stop moving, right? Brownian motion happens because we're powered by the sun. So that's just kind of an interesting thing to me. I also want you to look at the size, right? So as this changes in size, oh, a couple other interesting statistics, and I messed one of these up, and I don't know which is the correct answer. This protein moves ridiculously fast. I think it's 5 meters a second. It might be 5 microns a second, but I'm pretty sure it's 5 meters a second, okay? That would be like us at our proportions, moving, I'm not sure which one's right, either 5,000 kilometers a second or 5 million kilometers a second. Okay? Either one is ridiculous sort of relative proportion. But what that means is that at that speed, it is able to contact every single molecule in a cell every couple of seconds, okay? So we don't need genes to do that, right? We always like to think about genes. We don't need genes to do that. These things are going to find what they need to find and interact with them in the proportion that they need to make these things happen. So life has some things working in its favor. You don't need genes, and that's something that people often talk about. Well, you needed a gene. Sometimes you don't need a gene. Physics is already there, and all you need to do is create a system that can perpetuate a change in entropy. That is truly likely what the beginning of life was a system that could perpetuate order that could then expand from there. And that's probably what happened. So as it changes in size, you can see they obviously move faster, right? So you can imagine if it's a small molecule kind of bumping and moving around, it's probably moving just as fast, okay? But it's changing direction much quicker. It can't kind of get through. A big thing might just sort of hit and spin around. So again, you can sort of follow here. Now, there's nothing driving these things. There's no brain behind them. But any single point is just going to randomly find its way around and bump into stuff, okay? And if it likes to be somewhere more, it will stay somewhere longer. Getting back to the good cell picture, this is reality. This is what's in our cell, right? Water molecules, proteins, mRNA. These things are moving around, bouncing around by all these water molecules and doing what they need to do. Just to show you that our bodies are so cool, these are microtubules, these are actin filaments. You can imagine that you can create a space where a protein bounces around in it, that its effective volume of distribution is tiny, right? Because it's only dissolved in the water molecules in its space. So what does that do to the effective concentration? If you're able to section off 0.1% of a cell and put all of your drug in there, what does that do to the effective concentration? Skyrockets it, right? That's why our body does things that don't work in glass. Our body can create these spaces that make things look like magic, and it's very fascinating. Okay, so that's the end of physics there. So like I said, fortunately, we are going to be able to really look at things on a bigger level than sort of looking at electrons and protons, right? So we're going to hopefully be able to sort of work at things that are not overwhelming to us. I just think that that's an awesome picture. So I don't have a bunch of time. Why don't we just do the discussion and stop? Boy, I'm not going to get anywhere with this stuff. I have like so many lectures. Do you all want to do this discussion or me to talk about chemistry for 5 minutes and then we'll wrap up? All right, we'll do the discussion. That makes sense. So you all have paper. So like I had talked about before, we want to live in the world of the cell, right? We want to be able to understand it, sort of its shape and its size. So I kind of want everybody to just kind of draw a cell on your sheet of paper. And how big is a cell, roughly? What sort of order are we talking about? You can draw it as a circle or as a square or whatever. It's three-dimensional. How big are we talking about?
So 10 to 30 microns.
How much?
10 to 30
10 to 30 microns. I love it. That's a great answer. That's a good answer. 10 to 100 microns. Most of our neurons, 20 microns, 30 microns, maybe 50 microns, right? But cells, that's the rough range of cells. So what are inside of cells? We haven't really gone over the biology much, but you guys know some of this.
Organelles.
Right, organelles. Okay, so we don't even need to talk about particular organelles, but how big is an organelle? A micron. Excellent. It's a micron. So kind of think about that. Draw it in there. Remember, a cell is going to be roughly the shape of this size of this room, a little bit bigger. A micron's what? Right? It's like this. Right? We can remember that. It's sort of floating around in this room. Right? What about DNA? How big is DNA? Tiny. How big is it? Let's just throw out some numbers. Is it bigger or smaller than an organelle? Okay, smaller. So we know it's less than 1 micron. So that's getting us in the order of what? nanometers. So guess how many nanometers? 10. That's absolutely, no, it's not, it's 2. No, what I'm getting at is that it's not about the specifics, right? I'm not testing you about the specifics. Her answer is correct in my mind, because what she was able to do is say, hey, I can understand this system. It's smaller than an organelle, and organelle is 1,000 nanometers. It's a good bit smaller, so 10. That is what's important, not knowing 2, right? If that was a test and I was grading it, I'd give her that point, right? Because that's the goal of this. I want you to be able to just think of relative terms, how things are going to bang into each other, and how they can practically kind of work. Okay, so let's think of something that you know of from medicine, and let's talk about its size and what it might be able to do. Or, I mean, throw something out. You know, you guys don't memorize these sizes, but we'll be able to guess at them. What do you want to guess the size of?
Eyeball.
An eyeball. Okay. Well, I guess if we're going to guess the size of an eyeball, that's on the macro level, right?
You want something smaller.
I was thinking about something small, but let's talk about the eyeball. This will be kind of useful, although it's a little bit tricky. Let's guess the size of an eyeball. Yeah, let's say 3 centimeters, and it's kind of a sphere, right? It's not a full sphere, so that makes it tricky, but if it were, we could guess how many cells were in it, right? How would we do that? Volume, and how, right? We would just do a volume conversion, right? So it allows us to make reasonable guesses, right? We don't have to just accept things. We can kind of think for ourselves when we see things and hear things. It allows us to give our 2 cents. It allows us to get a gestalt for things. Is this right? Is this not? Does this make sense? Does this not? What I'm trying to get you all to sort of see is that when people say things to you, and this is very true in medicine, sometimes if you stop and think about it, you're like, whoa, whoa, whoa. Let's give up tradition a bit and question this, because that doesn't make sense. And that's, I don't know, and this doesn't make sense. I want those to be like 2 phrases you're very familiar with. Because I say that all the time, right? Like, that is what this is about. Finding what we can figure out on our own, questioning things, finding out truth. That's kind of what the goal of this is. All right. So let's think about, you know, what other molecular machinery, whether it be molecular machinery or molecules or whatever, do we know? Let's think about it. We've got 2 minutes, so a couple will do. What are y'all's favorite molecules or proteins or cells or?
Golgi apparatus.
Golgi apparatus. Okay. What is the Golgi apparatus?
Wow. Good one.
That's excellent. Yeah. Let's talk about Golgi, right? Do you know how that was named?
Sir
That guy.
Golgi.
So Golgi.
Camillo Golgi. Was he knighted?
I believe so.
Okay, Sir Camillo Golgi.
Don't leave that up.
Is one of my favorite scientists. Okay, so do you all know Ramon Call? The father of neuroscience, the neuron doctrine?
We did not.
They beefed so hard. They shared the Nobel Prize and were just bashing each other on their Nobel Prize speeches. I would have paid so much money to sit there. In fact, so Golgi was wrong, right? But I think he was more right than Ramon Cajal in his, so right, when we go back and we look at these things, he was wrong in the sort of specifics, dotting the T's and crossing the I's. Dotting the I's and crossing the T's. But what he said is that the brain is a mush, kind of, right? It's a network. He has the reticular theory, which means, you know, net-like or whatever. And Ramon Cajal is like, no, it's individual neurons. But I said this, you know, at the last lecture. It is, but the brain's really a mush, okay? 1 million neurons in, 1 million neurons out, 100 billion neurons mushing. So the brain looks a lot more like a mush. So anyways, that's just my props to Camillo Golgi. How big do you think the Golgi apparatus is?
Half a micron.
Half a micron probably wide in its spaces, but it's huge, right? We'll talk about that later. It's got large sort of cisternae and lots, and we'll talk about why it's a lot of processing and sorting happens there. There's a lot of surface area to it, but it doesn't have a lot of volume, kind of like alveoli. All right, cool. Thanks, guys. I appreciate it. Do you guys have any questions before we wrap up?
That was awesome.
Cool. All right, thanks, guys.